Okay, I'll share my screen again. So let me know when you can see it.
Yep, I can see it. Yep.
Perfect. So I'll open an Excel. Okay. So what we have here, we have put in the formulas here, and so there's a standard deviation population, tolerance allowed on either side of mean. So you would hear different terms. Tolerance allowed on either side of mean or delta is the same value, that we have here. And then you calculate the alpha. Alpha here is 10%, which is that means confidence interval we have taken is 90%. So if I take alpha as 5%, population standard deviation is 2. So this is population standard deviation is 2. Tolerance allowed on either side of mean. Okay. So if I just put the values here, population standard deviation, we knew it is 2. You're still able to see the screen, right?
Hmm. Yep.
Okay. 0.5 mm is the mean diameter of fiber cable, and it says it differs by 0.55 mm. So this is the
Hmm.
value for tolerance allowed on either side of mean, and then
Hmm.
the alpha that we have taken, because we wanted 95% confidence. So alpha is 1 minus 95, which is 5%. We put
Hmm.
the figure here. It just calculated 61 as the sample size, right?
Hmm.
Right, we got 62 here, so it's one the same thing. Similarly, for discrete, and there are various sample size calculators available. You can find any sample size calculator online. The concept is this: it will take into account the z, alpha, proportion defective, and through that it will calculate the sample size. So P is 0.15, 95 representation. So, so here 0.05, 0.05, I had to convert into percentage, 5%.
Hmm.
Representation error, again alpha, which is 95%, CI is 5%, and
Hmm.
it has calculated a sample size for discrete data, which is 195.91, which is quite close to this one. So this is, you can use sample size calculators to calculate the sample size, or you can look in the, you can manually calculate. These are the formulas for calculating. So it will calculate proportion defective, proportion non-defective, and Z alpha by 2. So we will understand the concept of Z alpha by 2. So let me just quickly see. If you wanted to cover Minitab, the challenge is you don't have it installed right now. So So this is known as Z table, and there are various kind of Z table available. Table under the curve, area under the curve. So what is Z? Z is the so Z is the number of standard deviation you are able to fit between mean and the specification limit. So if you have, if you can fit 6 standard deviation either side, so then your sigma level would be equal to 6. But what if you are able to fit 5 standard deviation on one side and 4 standard deviation on the other side? Then what would you do? What is the calculation? How would you calculate the sigma level? So for that, we have something known as a Z value calculation. Okay, so this is the slide that I wanted to show you. Okay, so if you have a discrete data set, right, you would calculate defect, unit, opportunity, DPU, DPO, DPMO, right? But if you have a continuous data set, you would be able to calculate standard deviation and mean, and then instead of DPU, DPO, DPMO, you would calculate Z long term, Z short term, and process yield, right? There are various ways of calculating process sigma. So all this, from DPMO, you can calculate what is the sigma level of the process. There is DPMO to sigma conversion tables available. You can just look up the nearest DPMO value and you can take the sigma value from there. And here, we will just go through some of the, how do we calculate. I'm not going through DPMO because DPMO we have already done. This is DPMO to sigma multiple. So if you have 3.4, it's 6.01 sigma, right? Wherein if it is greater than or equal to 500,000, it's 1.5 sigma level. And so it has only this level. You might be able to find a DPMO table which goes more than 500,000 as well. So if you have a Z value, you would be able to convert it to a DPMO table. So you have a Z value right here, and this is Z short term. I will explain you what is short term and long term. So short term and long term, the difference is 1.5. So it says in long term process become more inefficient. So you need to add 1.5 sigma in a long term sigma to get the Z short term. So we will now calculate. I'll quickly show you the calculation for Z. The formula to use is Z is equal to mean, or that value that you're looking at, minus mu is mean, divided by standard deviation. So if you look at the formula, what we are trying to find out, whatever value you're trying to look at, if you deduct that value from mean, how many standard deviation you should be able to fit into that. So remember, we said if you have a 6 standard deviation between mean and the specification limit. So let's say this X is the specification limit minus mean, right? If you're able to fit 6 standard deviation, that means your process is working at a 6 sigma level. So this is a formula that is telling us that itself, isn't it? You with me, Scott?
Yes, I'm here.
Right. So are you able to follow the concept? So if this X is the specification limit and this is the average, mu is the average, right? So remember, initially we talked about that if you're able to fit 6 standard deviation between the mean and the nearest specification limit, your process is working at a 6 sigma level.
Right.
Right. So if you look at the formula here, it is saying the specification limit minus mean. If you fit in standard deviation, what is the value you should get? So ideally you should get value of 6 if it's a 6 sigma process,
Right.
right?
Correct.
Okay, so this is what the formula is telling us. So let's go through an example to understand this.
Mm-hmm.
Animations are all over the place, so ignore that. So it is found that the time taken to prepare a specific type of report follows a normal distribution with a mean of 250 minutes and and I just yawned. So and a standard deviation of 23. Okay,
Mm-hmm.
what we want to find out is what is the probability that the next report will be prepared within 300 minutes. Okay, so remember, so what we are saying is 250 is the mean,
Mm-hmm.
and what we are trying to find out, what is the chance that next report will be prepared, or probability of that the next report will be prepared within 300 minutes, which should be right here, yeah, greater than 250, right? Scott, you there?
Right. There's 50. Yep. Yeah, I'm here.
Right?
50 in between.
Yes. So the formula, if you notice, if you would remember the formula that we saw, it is x minus mu by standard deviation to calculate z. Now, to calculate probability, we need to calculate z. Okay, z at this particular level, which is at 300. So the x
Mm-hmm.
here, what is the value that we are trying to find out? 300.
Mm-hmm.
So the formula would will be 300 minus 250 by 23. 23 is the standard deviation.
Mm-hmm.
So we got the value of z as 2.17. Right? Are we? Are you with me till now? Go
Yeah,
ahead.
I get that calculation, but is that the likelihood? It'll be. That's not the answer.
No, that's not the answer.
Yeah.
We will get the answer when we look up this particular value. So this is telling us between 300 and 250, how many standard deviations can I fit in?
Oh, yeah. Okay. 2.17.
Right?
Okay.
So it is telling us 2.17 standard deviation.
Mm-hmm.
Now we know that we can fit in 2.17 standard deviation. From this 2.17 standard deviation, we will calculate the probability. How we would do that? We would look in the Z table, Z distribution table. And I have okay, it's right here. So this is the Z that I have, Z table that I have. It is called Z table area under the curve. Okay, how we need to look at, so the value, what is the value that we wanted to find out? 2.17, right?
Right.
So where is 2? So this is the value for Z, right? So this is 2 right here.
Mm-hmm.
So, and this portion right here, these are the columns for up to 2 decimal places. So for example, how you read it, this value is 0.00, this value is 0.01. So if we come here, this value is 0.10, this value is 0.11, this value is 0.12, 0.13, so on and so forth. Right? This is how you would read it. So we wanted to find out 2.17. So 2.1, 2.10,
and 7, 98.
right?
98.4, yeah.
So 98.4, sorry, 0.9849966631. Yeah.
Right.
Okay, let's go back. 1 second. Presentation is stuck. What I've done is I have copied it. Okay. I've got it where I wanted. Let me just go back. Okay. So remember the value that we got was 0.98499,
Mm-hmm.
right? So,
Mm-hmm.
so if you convert into percentage, it'll be 98.5% probability
Mm-hmm.
that the next report will be able to accomplish the next report within 300 seconds. Why 300? Because from this point here, it tells us on its left hand side how much is the area under the curve. So how it is read is whatever point that we have from here to here, it reads you know, the area under the curve,
Okay.
right? You okay with this? Shall I move on to the next one? Okay. So now another one. Same example. What we're trying to find out the time taken to prepare a specific type of report with a mean of 250 minutes, standard deviation of 23. Right? What is the probability that the next report will take more than 280 minutes? So remember, in earlier one, it was up to 300 minutes. It was from this point till here. Now it is saying what is the probability that it will take more than 200 minutes. So if it's 280 here, it wants to calculate the probability of this particular area. So remember, entire area under the curve would always be 1, this 100%.
Right.
Okay. What we were able to find out between this and 300, it was 98.5%. We want to find out within this area, what we need to do, 100 minus 98.5%. We'll get this area.
Right.
You with me?
Right. Yep.
Okay. So, but this was for 300, right? So we would need to calculate what is the value for 280, and then we deducted from 1. So let's try to do that. Let us see. So this is the process that we have. Mean exactly at the center, 250.
Right.
Now there's a line for 280.
I got
right?
1.30.
Oh, you got 1.30? Okay.
Is that right?
Absolutely, bang on. I should have sent you the Z table as well. You would have made my job easier.
Yeah, send me the Z table. I would.
I will. Just give me a second. Okay, can you? Okay, I did not copy the right one. Oh, it's okay. 1 second. Copy pasting error. Right here. I wanted to copy this one as well. Okay. So what is the value?
1.30 is 93.1.
Yeah.
So
93.1. Okay.
Yeah.
Okay. Area under the curve is this much. So 1 minus 93.1 is 9.68.
Yep.
Right. So you are able to calculate the probability that the next report will be greater than 200 minutes is 9.68%. Okay. Now, okay. Like I said, my animations are all over the place. So.
Whoa.
So now what we're trying to do is trying to calculate the probability between these 2 points, 216 and 273.
Okay.
Okay.
So
So we know if we calculate it till here, it will give us this value. Till 216, this minus 1.47, it will give us area under the curve towards left hand side.
okay.
Right, and area under the curve till here will give us this entire area. So where I have Z1, which is 273, if I calculate the Z upper, I've got 1. So 1 is giving me from this point till here. So this is a point. So 1 is covering this much area.
Right.
Right, and Z2 is covering this much area.
How?
Right, from here to here.
260. Right. Yep. Okay. I got that. I'm there.
So if I want to calculate area between Z2 and Z1,
Take
it
your
will be
Z2
Z1
minus your Z1. Yeah.
right, Z1 minus Z2.
Yep.
Right, so I will get the probability that the next report will take between 216 to 273 minutes. So Z upper, if I put the figures in the formula, 273 minus 250 by 23 is 1.
1 is your
if you look here,
0.84.
0.841, which is right here. Now area covered by Z2, area covered by Z2
1.47
is minus 147. Okay, now we don't have minus 147 here, so let's calculate. It's not a negative, right? So let's calculate 1.47, and we will deduct it by 1. We will get minus value for minus 1.47. So it's 1.47 is right here, 0.9292, which is this value. 1 minus 0.9292 is 0.0707. Right?
1, 3, 4,
So 0.841 minus 0.0707, it gives us 0.7705, which is 77.05%.
Okay.
Right? Are you able to follow?
Yes.
Okay. Perfect.
That's a lot, but yes.
Oh yes, yes. It's gonna get a bit complicated.
Do I have to understand the concept, or do I have to do the math?
Which is okay, as long as you're able to understand the concept. Maths is fine. We have Minitab for that, so you don't worry about it.
Okay.
Right. So the concept is, if you have the value for Z, right? Not the Z. So if you have the mean, if you have the standard deviation, and if you want to calculate the probability, you would be able to do that. You know, if you have the mean and the standard deviation values. So you look at Z table, and through that you would be able to calculate the probability. Okay, so this is calculating the probability. Now, you know, if we want to calculate the Z value or the sigma value, how would we do that? So there are two kind of specifications. We have an upper specification and we have a lower specification limit. Okay, so the concept again remains the same. You know, we need to calculate how many standard deviations we can fit in between the upper specification and the mean, and the lower specification and the mean. Okay, so these are the formulas that you would use. Let's take up an example and do the calculation. We have a bottling plant of a soft drink company, and here it has given a specification that outer diameter of bottling cap should be maximum 11 mm and not less than 8.5 mm. Okay, so this is the specification. So how much is the upper specification, Scott?
11.
And lower is 8.50.
Right.
Right? And the mean,
Right.
we have the mean is 10 mm and standard deviation as 0.43 mm. Right? So let's calculate Z with respect to upper specification limit. So 11 minus 10 by 0.43, which is 2.32. And Z LSL is 10 minus 8.5 by 43, which is 3.49. So let me ask you a question, Scott, just to check understanding. When we say Z USL is equal to 2.32, what do we mean?
The upper limit will fit 2.3 standard deviations in it.
Absolutely. Upper limit and mean would fit 2.32 standard deviation. And with lower limit, it will fit 3.49 standard deviation. Right? So the process...
Curve's longer on the lower side than the higher side.
Right. Not the curve, okay. But we have process. The process that we have is more robust on the lower side with than the upper side. Right, because we are able to fit more standard deviations there.
Right.
Okay, so if I want to show it, I don't know if I've. Sorry. Okay, it's not there. So just to show it to you, just give me a second. I'll. What we are saying is, let's say this is a process. Where there's a bell curve. Right, now what we're saying is 10 mm is the mean. So let me just draw the line. Look, what was that?
There's your 10.
This is 10 mm. Okay. So let me write it here. 10 mm. We had upper specification limit at 11, right?
11 was the upper.
11 is the upper. Okay.
8.5 is the lower.
8.5 is the lower. So what we're saying is this right here is the specification given to us by the customer. So let me just is a specification given to us by the customer. Okay, so between this point and this point.
Mhm.
Between these 2 points, what I've calculated is I can fit 3.49 standard deviations.
Mhm.
3.49 standard deviations. Okay. Now between this point, so it is something like this. I can fit in, how much was the standard deviation? 2 point?
2 point something.
2.32. Between this and this, I can fit in 2.32 standard deviation.
Mhm.
Okay. This is the specification limit. Okay. So what do you think is the probability? Where would I make the maximum defects?
Make the maximum defects on the low side between point 8.5 and 10. Or where do
Right.
we make the? Oh, where do we make the maximum defects? After 11? Well, according to the
After,
bell curve, it's after 11, but
yeah. So let's say I remove this one. Okay. Now tell me.
we make the maximum between 8.5 and 10
Why?
on the low side
Yeah. Why do you say that?
because we can put 3 standard deviations versus 2 standard deviations.
So standard deviation would mean that you have more space here
Right.
between the specification given to you by the customer and the
Mhm.
mean. When you have more space, that means you have more leeway of defaulting here. So remember, more leeway of defaulting. That means, uh, you know,
More,
yeah, more buffer area here as compared to this
right.
area,
Right.
right? So imagine if the okay, if the so if we know anything which goes beyond this red line is going to be defect, right? So let me say that if the standard deviation instead of 2.32, let me say it would have been 1. What that means
Mhm.
is it would have been somewhere over here. Okay, if it's
Okay.
only 1 standard deviation, that means it's very near to the mean.
Mhm.
Okay,
So it's more
because
likely to have
more likely to
an
have a
error
defect here, right?
defect.
Because there is very less chances of variation,
Okay.
right? So the more standard deviation that I have in any side would make the process more robust. So if I go
Okay.
back to the bell curve and replant the image here, so ideally it should look something like this: 2.59 standard
Mhm.
deviation.
Okay. Yeah, that makes sense.
Right? So the more and if the standard deviation increases in either side, in both the sides, so let's say it increased to 5 here
Mhm.
and it increases to 6 here.
Mhm.
And what will happen is it will become something like this. middle path would keep on increasing and the
Mhm.
spread would reduce, right? Because 6 standard deviation I can fit here between the mean and the lower specification limit now, and
Mhm.
between mean and upper I can fit 5 standard deviations here,
Mhm.
right? So what is happening? The curve which was like spread, now I've reduced the variation further. See, if the standard deviation is reducing, the spread of the process would reduce, right? The specifications would remain exactly at where they were earlier.
Mhm.
So we are reaching at the situation of pilot B here, where everything is close knitted. So it will keep on reducing. The standard deviation that I can fit in would keep on increasing. Scott, you able to follow?
Yes. Yep.
Okay. So this is the concept, right? So that's the reason why we say process is more robust toward lower specification limit, because
Mhm.
we have more standard deviation that we can fit between mean and the specification limit.
Right.
Okay. Now let's
Mhm.
see how we calculate the Z value. So Z USL is 2.32. Now we would again need to look up the Z table. Now this time it is gonna be a different one. We'll look at this one. So 2.32.